sometimes when we're performing a titration, we don't necessarily always just want to use an indicator. Sometimes we want to use something that can actually monitor our pH. So let's go back and set up our titration one more time. But this time, instead of just plain old using an indicator, we're going to use a pH probe. And the way that we're going to set this particular titration up is inside of the burette, we're going to load it up with a standard solution, a known molarity of base. And down at the bottom, our analyte is going to be our acid. Now, since our pH wand is normally down in that Erlenmeyer flask, or sometimes even a beaker, just to try and make everything fit, it's going to be sunk inside of a solution of acid. And if you remember from before, acids have a pH below 7. So we're going to be recording a pretty low pH. Now, what's kind of neat about a pH probe is that you can actually graph your information as a function of how much of your standard solution you add in. I can graph pH versus the base that I'm adding in. And this is kind of what it looks like. Now, this graph is what we typically refer to as a titration curve. You'll see that in the beginning part of the reaction, the pH is extremely low because it's, again, sunk inside of a base solution. So we'll add in a little bit more and a little bit more base until suddenly something very interesting happens. My pH wand records a pH of 7. Now that's neutral, and that point in the titration curve has a very specific name. We call it the equivalence point. Now, what's equal about the equivalence point is the number of moles of acid and base. So there's no more acid and there's no more base. You've added exactly the correct number of moles of each thing that they neutralize each other. And this is an extremely valuable point to have in as far as calculations and everything is concerned for titration, because that's exactly what we're kind of shooting for. Now, another interesting point is going to happen if we continue past the equivalence point. At some magical point, all of a sudden, the pH will continue to rise, but you'll notice my solution just turned pink. And this happens at about a pH of 9. At pH of 9, my indicator turns color. It is past the equivalence point. This point also has a name, and you should remember this from the previous video. This is called the end point, and it's the point at which we end the titration. You'll notice that the end point and the equivalence point are not the same point. They happen at a full measure of 2 pH units different from each other. Again, the equivalence point is the best one to use for stoichiometry. It's the one we're really after, but oftentimes when we're using an indicator, the end point is the only one that we see. We have to use a pH wand to really see that equivalence point. Now, for purposes of stoichiometry, you need to know how much of that base you added in, and you can figure that out by using the titration curve. What you do is you drop just a vertical line down from the equivalence point down to the volume of the NaOH added. You can see that my line here, although it's not drawn perfectly, lines up almost with that 50 milliliters volume. We call that volume the equivalence volume, and that's the volume that you want to use for your stoichiometry problems. Well, what if we didn't have that pH wand and all we had going for us was the end point? What if all we could use was phenolphthalein? You could theoretically do the same exact thing. We'll draw another line down here. You can see that just populated in green. And we would call that volume, which is just a hair over 50, the end point volume. Do you notice a tremendous difference in those volumes? Because I sure don't. And honestly, I doubt that any stoichiometry problem with significant figures in mind would probably see the difference in those numbers either. So realistically, both of these points are okay to use in stoich, even though the equivalence point is what we're shooting for, because it shows us neutral and it shows us when everything is perfect. the endpoint is so close to it volume-wise that it's okay. Now let's continue with our titration. Let's actually push this to hot magenta and see what happens to the curve. And what you'll notice is it actually starts to plateau at higher and higher pHs. Now let's remember what's going on here. When our pH wand is recording a pH under 7, that means that there's still acid in the pot. That means that we've used up all of the base that we've dripped in, and we have leftover acid. That means that in this zone, anything that you can see here highlighted in green, the base is in fact the limiting reactant. The acid is in excess. In like manner, on the opposite side of the graph, in this zone, if you notice that you're recording high pHs, that means every speck of acid has gotten used up, and now we're adding in extra base. So base is in excess, whereas the acid is the limiting reactant. And for this class, the most important thing on this titration curve is that point right in the middle, where you don't have any excess reactant, any limiting reactant. We call that one point the equivalence point, and that's where you want to start your stoichiometry problems from.